we now continue developing the I2C core by wrapping an I2C master controller by wrapping circuit so that we can plug it in into the memory mapped I/O subsystem. So first we take a look at the suggested register map. So here's one in here. So in this particular register map, what I have is I have 3 different registers. If you remember, we have 32 total, but we're only utilizing 3. So some of them are read, some of them are write. I just packed all the read into one because it's pretty straightforward. So the read is actually the D out, and the D out is actually if you're receiving something from the I2C bus, you can read it from here. It's just generally 1 byte. The ready is just tells me that the controller is ready to do some new action, and the acknowledge is actually the acknowledge bit after you write something into a slave, it actually acknowledged it. You can actually read the acknowledge in here. The divisor is what we've seen before. It's actually so that we can control the I2C clock period or clock frequency. So based on the divisor, and the divisor is computed in the driver so that it actually generates these quarter of period numbers. Again, we can also write in DN, which is basically whatever it's the DN into the controller, so that this is the value that you want to send over to the slave, and it's actually the command is actually the 3-bit, whether it's write, start, or something like that. Okay, so let's take a look at the code, and in the code in here, it's really straightforward. So what we have is we have the standard signals in here, the chip select, the read and write for the MMIO, and then the external signals are exactly the same. It's actually output a try or in out try for the SDA and the S clock. Okay, so we take a look in here. What we have is we are going to store the divisor value into a register, and it's going to be a 16-bit one. And the right I2C and the right divisor in here, basically a few signals. So let's take a look at it. If you look at the register map, we only have 1 recording, so technically we don't need to do any multiplexing, but we have a couple of writings, so we need to do some decoding. So I'll jump directly into the read, and in the read you can see that all I'm doing is I'm just backing them. There's no need to use the address at all because I'm not multiplexing. Of course, the decoding happens in here. Actually, it happens in here. Okay, in the decoding I have a couple of things, and the first one is actually whether I'm writing to the divisor. And if I'm writing to the divisor, the chip select should be activated, the write should be activated, and the address that I'm trying to write to is offset 1, like the register map here suggests. And if that's happening, what you'll see in here is I'm just basically saving a value that I'm sending over the write data from the actual bus, the MMIO subsystem bus, so core, actually our FPRO bus, just storing it in there so that we can use it to generate the proper clock frequency for the S clock. What's more interesting is this write I2C. If you remember, this is the signal. If it's asserted, it writes the amount and writes the DN. It's generally asserted if you're trying to write the DN or the command. Basically, if you take a look at it in here, it's a chip select write and the address. If you're trying to write into address with offset number 2, it's basically just asserts it. And the signal is directly connected to the I2C. I know that I skipped this, but you need to instantiate an instance of the I2C controller, and what I've done in here is basically the divisor is connected to that divisor register we did, and the command in here is actually written into this particular, basically the command is just between 0 and 7 you take the write data, and the command is actually between 8 and 10, and the write I2C is actually directly connected, and it's actually included in here. The only signal we're not using from the controller is actually the done. So it's pretty straightforward here.